Okay. This is the day of. This is about an hour and 30 minutes from this being due. And I have a test tomorrow, so I kind of had to bring something. So before I do this project, I want to be completely transparent that for this code, while I have coded this and I have reviewed a lot of this code, I want to make transparent that I have used AI tools to accelerate my coding speed and or just my workflow. So a lot of the time, I will tell it what I want it to code, and then I go and verify each block by block, because obviously it's kind of useless if I don't know what's going on under the hood, right? But if that's a no-go, it's a breaker, I guess just don't give me the points for the project. But I'm not a very good liar, so I don't want to be like, oh, I coded everything from the ground up. This is a big project, and I'm doing it alone. I kind of needed the help of the internet and tools to speed me up a little. With that being said, I do know what's going on here, and I have, I have reviewed basically all of this code. Now, some of it at the end is very rushed because I am on a big time crunch. I have a math test tomorrow, and I'm kind of freaking out because that test is probably going to kill me. So, I have a stress strain simulation. I'm going to tell you the pros, the cons, kind of what I got to, what I didn't, what's good and what's bad and what's ugly, I guess. So here we imported the drive. So we're using Collab. This is cloud service. So I need to import it. That's pretty rudimentary stuff. And bring in my CSV. I only have one CSV. Again, time constraints really killed me on this project. This is essentially me digitizing an alloy from the Atlas of Stress Strain book. I can find the exact page it's off of if that's necessary. But for this case, we're just going to call it like an aluminum, thing. So you're reading the CSV. It plots the CSV out in this. This block does like the actual function definitions, and then you plot it out here, and there it is. There's stress strain. Then we calculate true stress strain because I decided to do that. Now that I'm looking at it, for the one I decided, well, I guess true stress strain will be better when I bring in, because I do want to finish this, bring in more data sets that are over different stresses, because I do know that I think the fact that it doesn't deviate much is more on the data set than like the truth. And so if you look here, I've already ran these, so I don't have to wait while we're doing this. This calculates the differential, basically, like it's 1.2% difference. So it's like nothing, more or less, but I did this to convince myself there was a difference, funny enough. So that's done. Young's modulus, you just calculate the slope. The assumption is the first few points are the slope, right, of the elastic part. You do the visual check. Easy peasy. 2%, so basically you draw a 2% offset slope, and where that slope, or 0.2%, sorry, and where that slope crosses the actual stress strain curve, that's your yield point. That's the whole point of the method. I found out about that through research. Then calculate stress or strain hardening, so that's the whole nother thing. Just to calculate hardening coefficients, which is for a model that we're about to use, and I'm about to explain that. So we're using something called a Holloman power law, which apparently is pretty accurate to the aluminum and like the kind of case we're in. And I would say, just off visual, things, not this one per se, but if you go down, and it actually shows you the power law down here. If you go down here, plotting it versus the actual points, not so bad. It's not perfect. And I think in a better world, I just have better CSV data, and I run, with, more digitized points, and I just run through the points, as opposed to generating a model. But to be fair, generating a model is more efficient than just having infinite amounts of points. But I guess it really depends on the real engineering application, as this is a little like visualization. I wasn't going to go through the depth of creating like 8 billion points in the digitized curve. So that is that. So you go down and a whole bunch of math and depth, and then it shows you, a big part of this is volume conservation. And so it actually does, one of the good things it does is it really does like actually calculate plastic like deformation and volume conservation so that the bar thins, right? Now this looks like nothing because it's such a little such a little strain, and honestly over basically all this animation here, I'll show you. You plot, it's gonna loop through. So blue is low stress, red is high stress, and you'll see that it moves, but it barely moves because I really think this data, this curve was not the curve to pick. But it does move and it does thin, and I will show you that here where I basically just multiplied by 5, and it's a little bit more visual. But this one shows you a bit better. I prefer this animation, despite the fact that technically it's slightly inaccurate, but it shows you the general behavior. But you can see that it doesn't just spurt out. The model does see, like, it really is incorporating the volume conservation. Sorry, I'm dying here. Of course I get sick right before the math test. No, it's earlier in the code, yeah. I labeled it. I don't know where it went. It literally says, like, calculate volume. Sorry. This is a lot of code. It's not here. I want to say volume conservation right here. Yeah. So it takes into account, sorry for that like long thing. I knew I had to be in the model, the kind of near the end visual model somewhere. Makes sense it's in the first that I put it. But it's volume, it's calculating basically the thinning of the rod. It's not just, my central whole point is that I'm not just like making the strain, like, bigger strain, bigger delta L, and the block just like moves out to infinity. There is volume conservation inputted into the equation. Hence why the block doesn't just become massive, and just like the huge delta L. So yeah, that is the project. It is very incomplete. I intend to complete it because it needs more than just this loop. I want to have it like, if you were to take a point here and go back, it should have a permanent damage. Like, it should be able to run specific experiments. Doing this loop kind of shows how it behaves. It's very good for going through the line, like from 0 to this, but it doesn't really show, like, if I go here and go back, what's the damage, So this model is not perfect, and I feel like maybe if I had a team, I would have been able to sort of perfect it a little better, but given the time constraints, this is what I have. And again, for the end, for transparency, I did use AI to assist in coding. So I primarily would either code things myself and then have it check for errors, or I would have it code certain blocks and I would go back and verify each block is doing what I think it does, right? So that was essentially my method of going through this whole thing. In the time span I did it, I'd be honest with you, I don't think I would have been able to figure out this from nothing, like, without it. So take that as you will. Again, if that's a no-go, no points, I'm doing fine, so it'll be all right. If that's cool, then great. Extra credit points, I guess. But that is my project in its whole. Thank you very much for listening through my Ramble Fest. I gotta get to studying. It was a great semester.